Thank you. Thanks. It's been a wonderful week, a wonderful conference, perfect organization, and it's my pleasure and also my honor to be speaking here at this new center and at this auditorium, which is named after one of the heroes in the history of black holes. So thank you very much to all the organizers. So what I'm going to talk about today is part of a program, some of the latest developments in a program that we started a bit over 2 years ago with a number of Japanese collaborators. In particular, I would like to highlight the role that these two postdocs, Ryotaku and Kentaro, have played, because they have been the driving force in this effort, and I wouldn't be here talking about this subject without their excellent work that they've done in this project. So it's going to be a talk about the black holes. Black holes, I think, in my opinion, are the most important objects in the theory of general relativity. But nevertheless, these black holes, they do not appear in the fundamental formulation of the theory. What you see is space-time gravitons. And the reason that they don't appear in the fundamental formulation of the theory is that they are nonlinear extended field configurations with complicated dynamics. They are so non-trivial that neither Einstein nor Schwarzschild ever got to learn that these objects are there in the theory. They died before them. Now, a very similar situation appears in another context, which is the context of Yang-Mills theories, where we have other objects which are very important and very interesting as well. These are the strings, which, again, they don't appear in the fundamental formulation of the theory, and that's because they are nonlinear extended field configurations with complicated dynamics. But of course, all of you know that there's a limit of the Yang-Mills theories. It's a limit that's non-trivial. You take one parameter which is not an obvious parameter at first, but when you think about it, then you realize that this parameter is there for you to play with. Now, when you take the rank of the gauge group to be very large, then these objects, strings, they become much simpler. They become, in fact, the most basic objects in this limit. Around this limit, the large n limit, you can reformulate the theory using a different set of variables, Walsh variables, and the dynamics of the strings becomes extremely simple, or at least much simpler than it is in the initial formulation of the theory. So can we do something similar for the theory of general relativity? Can we find a limit of general relativity in which black hole dynamics simplifies a lot? Well, what I'm going to try to argue in this talk is that this is what happens in the limit of large d. And if you think about it, well, if anyone can suggest to me any other parameter that we can take, say, for the vacuum Einstein equations, r mu nu equals 0, if there's any other parameter that we can use in order to try to simplify the theory, well, I'd like to know. But d is, I think, the natural parameter, the natural free parameter, dimensionless parameter in the theory of general relativity. So, as we will see, the theory will simplify, black hole physics will simplify, and then, well, you might ask yourself whether there's also the possibility of formulating the theory in a different way using black holes as basic objects, extended objects, but still basic objects. This is something that we don't have a full answer to yet, but, well, maybe the limit of large d, this is something that we can find for the theory. So I'm going to talk about black holes in d dimensions. The simplest solution for a black hole in d dimensions is the Tanger-Linde generalization of the Schwarzschild solution, which is a fairly straightforward extension to find. The only thing that you have to do is to change the power law fall-off of the gravitational field and stick in the appropriate number of dimensions there. And usually you would think that in this solution you have only one scale, that everything is determined by just this scale, which is the Schwarzschild radius, the horizon radius. But this is what happens only if you are working at d fixed. But what I'm going to do is to take d as a parameter that I can vary, and then, in this case, what we find is that there's at least one more scale. There can be more than one more scale appearing, but there's at least two scales hierarchically separated that are important in this limit. And this is due to the fact that the gravitational interaction becomes more and more localized close to the string horizon as the number of dimensions grow. So if you're in 4 dimensions, you have your black hole there with its horizon. All the gravitational field of the black hole is characterized by this same length scale, by R0. So you cannot really tell what is the black hole and what is the background, because the background has curvature on the same order as the region close to the horizon. But when D grows very large, what you find is that space-time around the black hole is becoming flatter and flatter, and there's a thin region of this extent. This I'll explain in a bit more detail in a minute. There's a thin region where all the gravitational field of the black hole is concentrated. So you can cleanly separate what is the black hole and its field and what is the background. Okay? And this is, as I said, it's due to the appearance of a new scale in the problem. Since we have a dimensionless parameter, which is D, then we can construct several different scales, and there are 2 particular scales which are important, which we can separate parametrically. And of course, having 2 scales which are widely separated, that we can separate, that's something that's very useful in physics because it's essentially what allows us to do effective field theories. So what do we have for the Schwarzschild solution in higher dimensions when D goes to infinity? Well, if we're considering that we're at some distance that's fixed as we take D to be large, then you see that in this case, well, this gravitational potential goes to 0 as D goes to infinity. So this means that space around this region is essentially flat. Gravitational field trivializes. This is what we call the far region. And as you can see, well, in this region, things become essentially boring. Things are more interesting if we're focusing on the region where the gravitational field remains finite. In order to keep this finite, so that this is of order 1 as D goes to infinity, then we have to be at a distance which is of this order away from the horizon. This is what we call the near horizon region. It's a thin sliver of this thickness around the horizon of the black hole. So what is the geometry that we get in this region? Well, this is the solution that we have. We want to keep this of order 1, so we define a new coordinate. We could choose some other name for it, but it's convenient to define it like this. I also rescale my time coordinate because this is a very thin region which is crossed very quickly, so I have to readjust my watch so that the time that it takes to cross it is finite. And then when I take these 2 quantities to be finite, I take D to infinity, and what metric do I get? Well, the geometry that I find is a geometry that's well known probably to most of you. It was first found in the context of string theory in the late 80s or early 90s by people here in the audience, in particular Spenta, Wadia, Gautam Mandal, Witten. They are all in this. So this is a solution that appears here. We didn't order it. We're doing just pure gravity in higher dimensions, and well, for some reason that we don't really understand fully well, we find this particular geometry which is important also in string theory. By the way, the fact that this solution appears in the limit D equals infinity of the Schwarzschild solution, that was also realized in the early 90s by Jiro Soda, even if it didn't attract any attention at that time. So we have this simple solution. For us, it won't be important, at least in this talk, it won't be important that this has some connection to string theory. But the only thing that's important is that this is a solution that has enhanced symmetry, and this means that it's going to be simpler to solve the equations in this background. If you're wondering, this is a solution to two-dimensional dilaton gravity with a particular coupling to the dilaton. The dilaton is the role of the dilaton. It's played by the radius of the sphere. And this new scale that I saw, we've seen appearing in this large D limit, it turns out to be what we would be identifying as the string length. So I said I'm not going to say more about whether there's any possible connection to string theory, to any effective string theory, because that's something that we're not really sure about. So I'm going just to stick to the classical physics of general relativity in this problem. Okay. Now, one of the things that we found, so this is a solution that appears in the large D limit of the Schwarzschild solution, but it turns out that we could conclude that this is also the universal geometry for all neutral non-extremal black holes in the limit of large D. And well, this is something that applies. When I say that it's universal, what I mean is that this geometry applies also when you consider black holes which are rotating. In the case where you have rotating, then you add another dimension to this two-dimensional black hole, and then you have some boost along that direction. But the geometry is locally the same. And if you have a cosmological constant, if you have a black hole, say in anti-de Sitter or de Sitter, then what this does to the solution, to the near horizon geometry, is a shift in the mass, which is something that doesn't change its geometry. So another question that we have this simplification of the geometry and near the horizon. The question is whether this is something that can be used, whether it's helpful in order to try to understand or to solve better black hole dynamics. In order to study this question, what we first did is to study, well, the simplest thing that we can do, black hole perturbations. And if you are going to study black hole perturbations, then you study typically the quasi-normal modes, the quasi-normal mode spectrum of the black hole. Well, what we found is that the large D limit of black hole physics, the quasi-normal mode spectrum is split into two different sets. This was first identified in numerical calculations performed by George with Oscar Diaz and Gavin Hartnett, and later we interpreted it in analytic terms, in the terms that I'm going to explain now. So what are these two sets? The two sets of quasi-normal modes, one of them is what I call boring modes. These are modes which have a frequency which scales like d in units of the black hole radius. And these modes are modes which are not normalizable in the near zone. So we have a well-defined near zone geometry, and then well, we can see whether some modes there satisfy the normalizability conditions, these modes don't. What these modes they describe, and that's the reason that I'm calling them boring modes, is just some oscillations of some hole. You take flat space, you draw some hole, and then you just throw some scalar oscillations into this hole, and then they will interact with the hole. And that's everything that these modes describe. And in particular, these modes, they are all stable. It's a spectrum that we can compute analytically, and we don't see anything interesting coming out of them. There's another set, a much smaller set of modes which capture more interesting physics. And these modes have a frequency which is of order 1 in units of the black hole radius. These modes are normalizable in this zone. So they are much closer to the horizon. They live entirely within the near horizon region, and their amplitude in the far region, that's exponentially small. So they are decoupled from this far zone. And these are the modes that capture the physics that you would be typically interested in. So if you have some black hole which for some reason you suspect that it's going to be unstable, then you should look for modes in this set. And also, for instance, the hydrodynamic modes of ADS black brains also fall in this class. So, well, we can use the separation. It turns out that these modes, we can easily compute them in the 1/d expansion quite efficiently, up to fairly high orders, and there are several problems that we have solved in this way. I'm not giving you the details of them, but we have found analytical expressions for, say, the quasi-normal modes of Schwarzschild black holes, possibly in anti-de Sitter or de Sitter. We have also studied analytically the perturbative Greuel-Laflamme instability of black brains and instabilities that appear in higher dimensional black holes when they are rotating very fast. So this we have solved analytically. You may want to ask whether, well, how well we are doing in these calculations when we compare to explicit calculations that people have performed, say, in d = 4 or in low dimensions. Well, that's I think it's a good question for the question period if you are interested, but since my time is limited, I'm going to move now to not just doing perturbations, but I want to solve fully nonlinear problems in black hole physics in the limit of large D. So what's the name of the game here? Well, what we want to do is essentially to replace the black hole by some surface in an empty background. And this is something that's natural in this limit because, as I said, the limit of large D, the gravitational field of the black hole gets concentrated very close to the horizon. So in the limit, we can replace just this black hole with some surface that we're drawing in the background. But of course, we cannot draw just any random surface in the background and say that this is a black hole. The black hole, its shape and its properties, that's determined by the Einstein equation. So there should be some effective set of equations that tell you what kind of surface you can take in this background. Now, this is an effective theory of black holes in the large limit, because what we're doing in this case, well, we're solving the Einstein, we have to solve the Einstein equations in the near horizon region. That's kind of like, say, integrating out short wavelength modes. And then what we get is an effective theory. It's an effective theory for these surfaces, which is the effective theory for what I was describing earlier, these low frequency decoupling modes. So that's something that we can do. What allows us to solve the problem, to set up this effective theory, is the fact that we have a separation between gradients in different directions. We have a hierarchy between gradients. So in the large limit, what we have is that the gradients in directions orthogonal to the horizon, these are gradients which are very large. Thank you. And then we are going to consider that the gradients in directions along the horizon, and this includes in particular also gradients in the time direction, these gradients are much smaller. They could be one, they could also be, in some cases we need them to be square root of d, but what they have to be, gradients along the horizon, they have to be much smaller than the radial gradients, which are the order d. So, well, I'm not going to give too many details. This is the most heavy equation in this slide in this talk. What we set up is some metric ansatz that's designed to capture the fact that in the radial direction we're going to have large gradients. Then this is kind of similar. It's not the same as Gaussian coordinates, but then we can decompose the Einstein equations neatly into directions along the horizon and directions transverse to the horizon. So we get an equation for the extrinsic curvature. We can write down the equations in terms of extrinsic curvatures. This is like, if you're familiar with the Hamiltonian formulation of general relativity, you can recognize as the evolution equation, and these are the constraint equations, which are independent of the radius. So we solve them, plug them. We can solve them in a way that's not too complicated, and get, at the end of the day, some effective equations for well, the collective variables of the black hole. We have done this explicitly. We have done this in generality for stationary configurations. That's not time dynamical. We impose that we have some time-like Killing vector, and we have also solved them not in full generality, but in particular cases for some time-dependent systems. Now, I have to say that, well, at the same time that we put out this paper, there appeared also another paper by a group here in India. And I think I can only describe this paper as an impressive piece of work. And some of you may have heard about it in yesterday's talk by Sai Anthony. We're still not sure. I mean, the formulations look different, and we still have to compare notes to decide, well, the formulations should be equivalent in some way, even if we are not sure in what precise way they are related. So what we find by solving for stationary configurations is something that's very simple. What we find is that black holes are soap bubbles. And this is an idea that ever since I was a student, an undergraduate student, I heard that black holes in some sense of horizons behave like soap bubbles. Now we're proving this. We're proving this in an explicit way because the equation that we find, that this surface that we cut in this background, what it has to satisfy is an equation that's also well known for those of you who have ever played with soap films. So the equation is telling us that this surface, this is the extrinsic curvature, the trace of the extrinsic curvature of this surface has to be equal to something that's, well, if we didn't have this factor, this would be constant. So the terms here, so we have the trace of the extrinsic curvature. This is a redshift factor. As you may remember that I said that rotation appears as some local boost along the horizon. So here, this is a Lorentz boost. And we may also have a gravitational redshift, because if your black hole, say, is in anti-de Sitter space, then there's a gravitational field acting on it. So everything, all of these effects are encoded in here. And this constant that naturally appears is the surface gravity. So if we have a static black hole, then this is just k equals constant, which is the equation that all soap bubbles, static soap bubbles satisfy. And if you have rotation, then it's a simple generalization of it. So first thing that you check. Well, we checked in detail that the static soap bubble in a Minkowski background, it reproduces the properties of the Schwarzschild solution, also in anti-de Sitter space, and if you put this rotating, then you reproduce the properties of higher dimensional rotating black holes, which are known explicitly. This is fairly simple, and this is nothing new, but then we've applied this formalism also to find new classes of solutions, or at least classes of solutions that were not known in closed analytic form. And one of them, a rather non-trivial class of solutions, is what's known as black droplets. These are black holes that consider that you're in Poincare ADS spacetime, then you put a black hole that extends all the way to the boundary, and then what you try to find what's the shape of this black hole. This is a problem that it remained open for many years, and it was finally resolved by these people by constructing, writing down some code, a specific code for solving the problem, and then solving it numerically. So this is a good problem for us, because it's a problem where we can, for us, it's just determining what's the shape, the radius of this black hole as a function of this holographic coordinate. So if we take this equation, that the extensive curvature trace has to be constant up to the gravitational redshift, then we get a set of nonlinear ordinary differential equations. Well, these equations we also have to solve them numerically. So like these guys, we cannot solve the problem fully analytically, but we have to solve them numerically. But the numerical solution, well, the code that I have to write down to solve the equations, it's much simpler than theirs. It's just this. You can do this in your computers now if you want to. It's fairly simple, and then you get solutions. You get one solution after the other. We have a one-parameter family of solutions. You just change one of the boundary conditions, and then you get different solutions for the black droplets. Okay. So these are for stationary solutions, but we can also do, as I said, we have also developed the formalism for some particular classes of time-dependent systems. And one particular class which is interesting, because it's not so very well understood in all its details, is the problem of the evolution and the endpoint of the black string stability. This is the problem. This is a problem that was first studied by Ruth Gregory and Ray LaFlamme in the early 90s. If you have a black string, you perturb it a little bit. What they found is that this has an unstable mode which develops ripples along the horizon. But then you may ask yourselves, well, what does this evolve into as you let time go? Do the ripples continue to grow? Do they decay? Does this end at some stable configuration, or does it proceed without end? Well, a few years ago, Louis Lerner and Franz Pretorius decided to tackle this problem and put it in a computer. So what they did is take a 5-dimensional black string. Actually, they did it for a green string, but it's the same. And then, so they put it in a computer. It's a green, and the background is Schwarz, so it's a green Schwarz string. Sorry about that. So what they did is they let it evolve, and then they found that, well, the evolution doesn't seem to end at any stable final configuration. They let it evolve, develops these blobs, which continue evolving. So this is very nice. This was a landmark calculation, landmark result in the application of numerical relativity beyond astrophysics. So what's the problem with this calculation? Well, the problem is this, that it takes, well, first you have to write a code, test it, takes a while, and then you have to get hold of powerful computers and then run them on 2 months continuously on 100 processors. So that's something, this calculation nobody has reproduced, and nobody has performed a similar calculation for other situations that we might be interested in. Because there are other instances where we think that this Gregory-LaFlamme instability should be important, and we're not sure what the nonlinear evolution is. So this gives us, this is one good motivation to get, to try to develop other methods, because there are open questions that we don't know the answer to. For instance, they got this system, well, this is evolving, developing more and more structure as time goes on. Can we understand, can we develop some analytical understanding or semi-analytical understanding of what is this late time asymptotic configuration? And if we change the parameters in the problem, do we get the same evolution? Do we get the same kind of final evolution, asymptotic evolution? Well, at least for in this case, we had good evidence that this is not the case. If we consider the number of dimensions as a parameter, then it's been known for years, at least since Eugene Sorkin first realized, that if we increase the number of dimensions beyond some value, and if you ask yourselves what kind of dimension is this, well, just think that we're taking D as a continuous parameter, then it was already realized that for low dimensions, since the weak non-uniformity decreases the area, a non-uniform black string couldn't be an endpoint. But if the number of dimensions is sufficiently large, then if you include a little non-uniformity, then this increases the area, and then there's a chance that a non-uniform black string could be the endpoint. So what we've done is to obtain effective equations in the leading large delimit for this system. The equations can be written in terms of some collective variables. One of them is what you would call the mass density, or the energy density of the black string, which also measures the local area, and the momentum density of the black string. That's a boost along the string. And the set of equations that we get is this, which is fairly simple. It's just two equations. These sides resemble the heat equation, but you have some nonlinearities over here. So these equations are simple enough that now that I'm becoming a numerical expert, I can also try to solve them. This is my code. Again, that's something that, if you want, you can get results before I'm done with this talk, because it's just this line of ND solve that you have to solve. And it takes about a second, depending on how quick, how fast your computer is, how much resolution you want to produce a solution. So I'm just going to show you that I can also produce movies. So that's a simulation that takes about 1 second to produce. And also the movie comes with it within that second. Okay. And what we see is that the evolution ends, as had been conjectured, at a stable non-uniform black string, which is, by the way, something that Gary Horowitz with Ken Maeda had conjectured early on, even if independently of the number of dimensions, but now we see it realized in this large delimit. You can run as many simulations as you want, and so in 10 minutes you can have, you can explore the parameter space very easily. So now, since my chairman is telling me that my time is up, then I will finish with just one conclusion, which is that I think that that's the main conclusion of the work that we've been doing for the last 2 years. We've learned that this 1 over the expansion is extremely well tailored to dealing with the dynamics of black hole horizons. And I think it's probably the best method that I know of for solving the dynamics of black hole horizons in generality. And well, with this, I'll stop, and thank you for your attention.
Question?
So there were arguments long ago, I think by Andreas Strominger, among others, that the theory gets more classical in this limit as well, because the angular momentum integrals have this 1 over gamma of d over 2 factor. Is that something that you would, is that true, that it becomes more classical, that you can ignore the quantum effects?
I think that we're not seeing anything like that. So we're focusing on black hole horizons here. And I'm not sure whether, so what I recall from Andy's paper from the early 80s is that, so I think that the idea was to take, in the same way that N is the rank of the gauge group in gauge theories, D would be increasing the gauge group in general relativity. So you might get some simplification in the diagrams. I'm not sure if you can correct me if what I'm saying is wrong. And try to see whether you, well, by simplifying the diagrams, whether you would get something like a topological expansion in diagrams or so on. This didn't happen. That was essentially the theory of Feynman diagrams around, say, flat space. That's not what we're doing, because I'm not sure whether that's going in any useful direction. But I may be wrong. What we're doing is something that, in principle, it sounds completely different. The angular integrals, I don't think that we're seeing anything like that in our calculations. Quantum effects, that's something that I can also say more things about. But, well, usually for a quantum field theory going to a large number of dimensions, that's a bad idea. But close to the black hole, we get some simplifications. And that's something that we're still exploring.
Yeah, actually, I wanted to ask you something about that. If you take the Einstein action, you pick up the method of dividing matrix. There's a single trace term and a double trace term. And you might think that at large D, that's certainly what happens with one diagram model.
Yeah.
That the double trace term would dominate. Now, long ago, I was just interested in quantum diagrams, and it didn't seem to be very useful.
Yeah.
But this is a very different problem.
Yeah.
And so my question is, could it be possible that if you just take the Einstein action and throw away the single trace term, which is smaller than the double trace term, that there's a simpler theory of general relativity in higher dimensions of which your black holes are.
Yeah, I'm not sure. Yeah, yeah. Of course, when you take d to infinity, you also have to decide how the different terms in the equations are going to scale with d, right?
Right.
And that takes you to one limit or the other. It's like in Young-Mills theories, you can take the number of colors to infinity, keeping the number of flavors finite or not,
Right.
and then you get the different behaviors. So I don't know if what you're suggesting is useful or not, because we haven't explored it. I had a quick look, and I didn't see it going clearly anywhere. Now, the way that I wrote the equations there in this decomposition where we separated the radial direction, in that case, you can see traces, and then you can see different terms scaling different ways with a number of dimensions, and that's helpful. That's essentially what we're doing. We're rewriting the equations in a way where some traces are apparent, on how some terms behave, it's apparent, and then we can throw some of them to leading order and then include them at higher orders and so on. So that's the useful way of rewriting the equations that we found. Maybe in the formulation that Shiraz and collaborators are pursuing, things look differently, but that's what I can say.
Okay, I think we should move on. Let's thank the speaker.